What is common knowledge today took our ancestors centuries to uncover. Today, I want to take you on the long but exciting journey of our ancestors trying to understand stars. It's an obvious fact that the Sun is the center of the solar system, but it took us years to accept this when Nicholas Copernicus first gave us this idea. In the wise words of B.F. Skinner, science is a willingness to accept facts, even when they are opposed to our wishes. As we continue through this journey, you will see widely accepted theories that seem absurd now. One of them is the fact that people thought that the sun was made of coal. They thought that the sun was a big ball of burning coal. This theory was dismissed when someone did the math and found out how absurd this idea was, as if the sun was made of coal, it would only last 5,000 years, and archaeologists found evidences that humans were way older than 5,000 years. The first steps we took towards modern science and astronomy is when Fraunhofer, a glassmaker, made a prism which split light into rainbows of colors. I know that sounds useless and a toy for kids, but this piece of glass is very important, and everything that happens after this point only occurs because of this piece of glass. He was curious and pointed one of these towards the sun and found out that some of the colors were missing from the rainbow. A couple of years later, after his untimely death, Kirchhoff and Bunsen were testing their new invention, the Bunsen burner. They burnt elements on it and found out that every element burnt into a different color. They then recorded the wavelengths of each light emitted by the elements and found out that sodium burnt with an exact 589 nanometers. This exact wavelength was missing in the sun spectrograph rainbow. So, can it be possible that instead of elements emitting light in the sun, they were absorbing it? It was this invention of the prism that allowed the astronomers like Secchi to classify 4,000 stars into three categories, Roman numerals for 1, 2, and 3. He wasn't the only one who was interested in classifying stars. Edward Pickering also classified 10,000 stars. William Mina Fleming did most of the calculations to classify these stars. Pickering and Fleming revised the Secchi's system to have more specific subclasses using alphabets. As you went through the alphabets, the absorption lines by hydrogen decreased. Some deemed this system too complex. One of them, Annie Jump Cannon, simplified this by sticking with the alphabets and dropping all of them except A, B, F, G, K, M, and O. Most of the stars fit into these, but some were halfway between each letter, for example between A and B, so she added numbers between them from 0 to 9. In this system, the Sun is a G2 star. But the question still remained, why do stars shine? Arthur Eddington proposed that the sun is powered by nuclear fusion. He said that hydrogen nuclei merged into helium. This produces energy to counterattack gravity. Hans Bethe later expanded on this with his theory that stars convert lighter elements into heavier elements. Yet, these theories didn't really explain everything going on. Again, Hans Bethe gave us a theory. He found out that stars could cycle through combining hydrogen and carbon, nitrogen and oxygen to finally make helium at the end. This is known as the CNO cycle, and in larger stars is a dominant way of making energy. One more question emerged. What happens when stars run out of hydrogen to fuse into helium? Fred Hoyle came to the rescue and said that it starts to collapse. This means that the core heats up and the pressure increases, which are the perfect conditions for helium to convert into carbon. Carbon burns with more energy, thus the stars expand, making it a red giant. This process of converting all the core into a heavier element keeps happening, with the core getting smaller and smaller until it reaches iron. Iron can't fuse because it requires more energy to fuse than you get out of it. Thus, it explodes, slowly ripping apart its upper atmosphere with a violent explosion. This theory tied up all the theories in a nice packed box. Now our attention shifted towards what happens to the star after it dies. We had already observed this, but we didn't know that stars we had found were the answer to this question. Ralph Fowler was studying these stars, white dwarfs, but he couldn't justify that these stars were so dense. So, using quantum mechanics, Ralph Fowler figured out that the densities of these white dwarfs could be explained if gravity has pushed down the matter so much that the electrons of the matter started to push back against gravity. Later, Shubhram and Chandrasekhar found that the maximum mass of these white dwarfs was 1.44 times the mass of the Sun. Although this idea was met with a lot of criticism because everyone thought that a star could only be powered by nuclear fusion. Arthur Eddington, remember him? He thought that it was absurd that there was a limit beyond which matter in a white dwarf could not resist the crush of gravity. 1 year after the discovery of neutrons, Fritz Zwicky and Walter Pardee proposed a star made completely from neutrons. Now we had an explanation of what happened after the limit of white dwarfs, but these guys were working on a different problem, explaining what was left behind in a supernova. They claimed that this was neutron stars. These stars would be supported by neutron degeneracy pressure, the same as white dwarfs, but instead of electrons, these were neutrons. But just like white dwarfs, the question still remained, is there a limit to neutron stars? This was tackled by Robert Oppenheimer. Yes, that one. He and his PhD student derived the mass limit of neutron stars, the Tolman-Oppenheimer-Wilcoff limit. Beyond this, they claimed that there was no laws in physics that could prevent the star to be crushed down into an infinitely small point, black holes. In 1967, Johann Sina Bell discovered the first pulsars, which are just fast-spinning neutron stars, although Arthur Eddington did not live to see the discovery.